Good afternoon. Thank you all for being here. Just to clarify, I'm an online MLIS student at the U of A, and I work at McGill in the music technology department. That's the dual affiliation there. So I'm just going to get right into it about the SIMSSA project here. Digitization has been a huge component of recent efforts on the part of libraries, museums, and archives to improve the accessibility and preservation of their holdings. These include online collections of written manuscripts, art, and musical scores, and many of them are in the public domain. Many of the text items are also processed using optical character recognition. While the quality available from a given institution varies a lot, the technology itself is fairly robust, thinking about Google Books making text search possible over many millions of pages. What we're doing at the SIMSSA Project is essentially making the same thing possible for notated music, taking images of scores, whether they're old chant manuscripts or Beethoven string quartets, and making them machine readable and searchable. This is the single interface for music score searching and analysis. This is a SSHRC partnership grant. We started in 2014, so we're just coming up on halfway through at the end of October. Ichiro Fujinaga at McGill University is the principal investigator. And among our partners is the British Library, the Bodleian Libraries at Oxford, the Bibliothèque Nationale de France, the Bavarian State Library, the New York Philharmonic Archives, the University of Pennsylvania Libraries, and the Harvard University Music Library. Are there any music librarians here today? Hooray. Okay. So today I'm going to give you an overview of the technologies that make this possible and explore the implications for libraries with digital collections and also the future of music analysis. For a quick overview, how it works. So a library digitizes their scores. We can do optical music recognition to process these images, allowing us to encode the music in a machine-readable format, in our case, one devised by the Music Encoding Initiative, so we use MEI. And then finally, search and analysis tools allowing users to search. So perhaps they could look for a particular melody or do a search for different chords or other combinations. And you can do this search in a single piece, over several pieces, perhaps from one composer, or querying dozens of works over hundreds of years. So to explain how this works, I'll address three major questions. One, how do we access the scores? Two, how can we teach computers to read musical scores? And three, how will music search and analysis work? First, how do we access the scores? Each library has their own online collection, perhaps their own image viewer, their own sign-in page, their own permissions, and so on. Something like IMSLP, the Internet Music Score Library Project, addresses this by taking scores that are in the public domain, uploading them, and hosting them directly. However, this often obscures the relationship to the original library's collection and also takes a lot of computing power. This is where the International Image Interoperability Framework comes in. I know there's a few other presentations talking about IIIF. So, IIIF is an API standard designed to promote better and easier access to online images such as those in libraries and museums. It provides specifications for creating a manifest for each image. This means all we have to host is the manifests pointing back to their host institutions. We do this at musiclibs.net, launched by Andrew Hankinson, a former SIMSSA postdoc and current software engineer at the Bodleian Libraries at Oxford. So here's musiclibs.net. Here on our MusicLibs homepage, you can see a random selection of thumbnails from some of the sources already on MusicLibs. They're a bit tiny, but you can see they're from the Internet Archive and our partner, the Bibliothèque Nationale de France. Currently, there's over 67,000 documents with many more on the way. However, with MusicLibs and IIIF solving the problem of how to gather all these images in one place, we still only have really nicely organized pictures. How can we teach computers to read musical scores? I've already mentioned optical character recognition, which can turn a picture of text into a machine-readable format such as XML. The analog for music is optical music recognition. So this makes sheet music machine-readable and puts it in a format such as MIDI, music XML, or MEI. And I mentioned the MEI format beforehand, and so it's a music encoding that allows something like that snippet of score on the left to be represented with the markup on the right. MEI is a kind of XML format based in part on the Text Encoding Initiative, or TEI. And so the MEI format lends itself particularly well to libraries and archives with specific details about the manuscript, such as illustrations and the location of objects on the page encoded along with more exclusively musical information. There are quite a few commercial options out there for optical music recognition. For example, Sibelius has PhotoScore, which some of our researchers have used to prepare pieces for analysis. However, these are largely designed to handle music that looks like this. So here we have a Schubert piano sonata and a pretty standard look for how the staff lines look, the clefs look, the notes look, and it's not handwritten. So this kind of OMR doesn't work on everything, but if we sit and wait, commercial OMR for these types of notation will improve. However, not all music notations are so popular. Many of our researchers study chant and early music, so we wanted to develop OMR that can handle something like this. So this is the Saltins antiphonal, and it lives at St. Mary's University in Halifax right now. And so we want to be able to read this kind of notation as well, and it's quite a different look from that. So SIMSSA's OMR, developed by our postdoc Jorge Calvo Zaragoza, reframes the OMR problem as document analysis. Previous competitions for OMR have focused on the best techniques for binarization and staff removal, but it turns out we can get even better results by being less domain-specific and letting the computer figure things out using machine learning. We start with labeled ground truths, a page or two from the document we wish to process with everything correctly labeled as part of the background, part of the text, part of the staff line, or part of a note. These ground truths are the basis for machine learning. First, we have to give the computer a bunch of stuff that, to the best of our knowledge, is correct. We developed Pixel.js to aid us in the creation of these ground truths. In this screenshot from Pixel, you can see that the OMR system has mostly classified things correctly. The staff lines are yellow, the text is blue, and the musical notes are in red. However, you can see in the notes in the middle, some of the pixels have been incorrectly classified. They're in blue. They pick them up as text. And so in Pixel.js, you can make these corrections quite quickly and as an integrated part of the OMR workflow that I'll talk a little bit more about later. So once we have all these corrected ground truths, we use machine learning to train our system using pixel-wise classification. And so this is the system developed by Jorge that I was talking about before. And so based on these ground truths, the computer determines the probability of a given pixel belonging to a category such as symbol, background, or staff. Then we run it on the rest of the document, figuring out what each pixel is likely to be. We've had a lot of success in tests with this method and are hoping to start large-scale processing of files this coming spring. It can work for any style as it learns from the ground truth images instead of depending on domain-specific heuristics. Next in the OMR workflow, we need to do pitch finding, and we can correct any misclassified symbols in our interactive classifier. So here, the green symbols on the left have been classified by a human, and then yellow is a guess from the classifier. And in the far left-hand column, the editor defines different classes of symbols. So you could make a new category, identify a few symbols as belonging to that, and then run it again with just that updated information. So you can improve the results as you go through the process, through interactive input. Then we do final corrections in our editor, neon.js. And so on the right hand, you can see the original images, or the original image with the results of the OMR process overlaid on top. On the left-hand side, you can drag sliders to change the opacity of either layer, making comparison between the original image and your end result pretty quick and easy. You can then insert missing notes or symbols, adjust staff lines, and create an MEI file that is faithful to the original manuscript. Currently, these tools are undergoing usability testing at McGill and Dalhousie, and all these tools combine into a single OMR workflow using a workflow manager called Rodan, developed in 2014 by Andrew Hankinson as part of his PhD. This workflow manager was originally conceived for this OMR process, but we also use it for music analysis problems now as well. Once all the tools in this workflow are ready, we can begin crowdsourced OMR correction. Our partner institutions and related communities can provide further feedback on our tools, but also participate in OMR correction on a larger scale. This means processing a huge volume of images, depending on user communities to correct the results and refine our processes, and iteratively increasing the accuracy of our methods. Now we have a format the computer can read. What are we going to do with it? How will music search and analysis work? Existing search of musical documents is limited to its metadata, and metadata and cataloging for different types of music can be tricky to do well or consistently. As well as metadata search, our tools will allow us to search the music itself. The first tool in this category is melodic search. This involves implementing various search algorithms that can find not only a simple string of notes, but variations on these appearances, including in more than one voice. This example from SIMSSA researcher David Garfinkel shows a piece of music on the left with some example queries on the right. Each of these queries would return a result in that piece depending on different parameters, so you can allow for some missing notes, or a different time duration, or different degrees of variation from the original melody. Symbolic music allows us to study music on a much larger scale. Instead of studying a single piece, Laboriously analyzing harmonies by hand, scholars can use computers to generate data about hundreds of pieces in one go. And so we have a kind of musicology involving corpus studies. And so a corpus study involves a large body of musical work in a single research project. For example, Schubert and Cummings' paper in 2015 uses a counterpoint app to study relationships between voices in the late Renaissance. So they borrow the concept of a 2-gram from textual analysis, looking at how different voice pairs move. So for example, in the boxed example, there's a unison, which is 2 voices on the same note, moving to the voices being a 1/6 apart. And so it's like studying the frequency of pairs of words appearing in English text, but taking that concept and looking at changing intervals between notes. And so you can look at stuff in terms of compositional style, in terms of what key it's in, all sorts of things like that. And so the number at the bottom of the triangle indicates the motion of the lowest note. And so studying these patterns can reveal a lot about the styles of different eras and composers. Similarly, this is a project I worked on with Karen Desmond and Sam Howes. Sam Howes was a SIMSSA PhD, and Karen is at Brandeis now, but she was with us as a postdoc for a while. And so we looked at the French motet repertory in the 14th century. And so this is a really important style change period for motets. And so we looked at about 65 motets, and so we wanted to look on a large scale how the treatment of different kinds of sonorities, different kinds of chords changed over this time period. And so this graph itself on the left, there's the 3 different groupings, so they all come from different codexes, and then the colors represent different kinds of sonorities. So instead of like a major or a minor chord in this era of music, you talk about like perfect, mixed, and imperfect, but it's a similar concept. And so in order to do this, we used the Rodin workflow that I talked about before, but this time as a music analysis workflow. And then in addition to that workflow, we had some custom Python scripts to further query all of our results together. And we can also use Python to like prototype tools that we might officially add into the analysis tools later. Claire Arthur's study compares a Renaissance theory treatise with some Renaissance compositional practice. Does it do what it's supposed to do? So she reads a bunch of rules for good counterpoint and then says, okay, I'm going to study a whole bunch of pieces and see if they actually follow these rules. And so this graph shows the frequency of occurrence of direct and parallel intervals, which are textures typically deemed undesirable, in relation to the number of voices in the texture. So the direct intervals on the bottom there seem to be okay as long as you hide them with a lot of other voices, and the parallel are consistently unpopular. Sorry, the direct is the one on top as it gets hidden in more voices because the x-axis represents an increase in the number of voices. Music analysis is a slow job without computers, and it's common for a research project to focus on a single piece of music or even a single chord. This change in scope allows us to consider a lot of new questions. Additionally, we've been doing some machine learning work on the analysis side of things as well. SIMSSA co-investigator Corey Mackay has developed a machine learning framework for analysis called JSymbolic 2, extracting musical features to aid with search and indexing or even predict who composed a given piece. This study here extracted features and then tried to guess the composer with pretty impressive results. The bar graph shows classification accuracy as a percentage on the y-axis and the composer group on the x-axis. Interestingly, the features that proved the most useful for consistently identifying composers aren't necessarily the ones we'd think to teach or analyze. Musicologists and theorists are pretty excited about these tools, and insights they generate about style and genre might also lead us to novel classification schemes, which can improve our search and maybe even our metadata in the future. We also see SIMSSA as a valuable resource for librarians, professional and amateur performers, educators, and anyone interested in taking these large collections of music and using the internet to make them more broadly accessible. Thank you.
Thanks for your presentation, Emily. I'm just wondering, I've heard of this project from music library circles before, and I'm wondering, because a lot of the examples are of very formalized musics that kind of have, standards of notation and are kind of, in a way, can be predictable in how you'd have the computer do the OMR and then how that, would feed into analysis. Are there any plans for expanding it for sort of non-standard kinds of music, popular music, for example, world musics?
Yeah, I guess there's a couple parts to that. The first is that our partners are music libraries, so to some extent we're working with what their holdings are. And so to the extent that they have digitized popular music, we can work with it. Another part of that is copyright. A lot of more recent music, you get in a lot of trouble if you put it up on the internet for free. And so to some extent, we have to work with older tools. Another part of that is that, yes, we do have postdocs who are interested in popular music and working on it, and doing things in relation to text and in relation to popular music and working with transcriptions, and that end of things as well. And another part of it is something like our OMR system. We can train it based on a page or two from any score. So if we did suddenly have access to a large pool of some other totally non-standard notation, we could say, here, have 3 pages of correctly labeled ground truths, and we could expand from there. So there's a few different reasons, some better than others, for not having that as a major focus, but that's sort of the gist of it.
In your talk, you gave one of my favorite phrases, which is ground truth, but I'm not very familiar particularly with a lot of music librarianship, but what I was really interested was that you used ground truth as like a text. So you're like comparing what the AAI thought is, what they thought the notes were compared to the actual text. I was just curious, at what point do you ever have someone come in and like try to listen to the music to see whether it sounds what it should sound like?
You mean in relation to like playing back what we've OMR'd kind of?
Yeah.
I guess for the most part, because you're working from a picture, trying to get to a picture, it's faster to compare it visually. But we can do playback with the MEI because it does have all the musical elements encoded. So like, for example, the Saltins antiphonal, there's an exhibit that we worked on at St. Mary's University where you can follow along and do an thing with interactive scores. But as far as actually testing for accuracy, one thing actually on the analysis side, we've talked about trying to do tests for if the MEI worked in relation to the sonorities. So if we know in this particular era, you're really unlikely to have really clashing dissonances on every downbeat, and the MEI file we just came out with has really clashing dissonances on every downbeat, probably something went wrong in there somewhere. So that's sort of closer to an aural thing, although in a lot of cases it's still faster to generate a big list of intervals than it is to listen to it. But yeah.
Thank you.
Thank you all so much.